Okay, let's get started. Today is going to be a fun day. We're going to cover a bunch of other execution paradigms that you haven't been exposed to probably, but that are really important. So last time, we're done with branch prediction now. There's more to cover in branch prediction, but if you're interested in the topic, you can look at the backup slides that I put. They're not extremely essential, but it's good to know for you. So I'm switching to VLIW, which is a concept, which is one of the execution paradigms. And remember that we're covering a bunch of execution paradigms. We've covered pipelining, out-of-order execution, data flow, superscalar execution. And now we're going to switch to VLIW. And we've also covered fine-grained multi-threading, but if you have time, I'm going to go over that again. But this depends on if you have time or not. And then today, we're going to go into systolic arrays and decoupled access and execute. And next week, we're going to cover data parallelism in a larger scale, SIMD processing, GPUs. Basically, you'll learn how modern graphics processing units work, which are essentially parallel processors that you have everywhere. There's a GPU in here also. Okay, so VLIW. This is one of the execution paradigms. It's actually analogous to superscalar. You know what superscalar is. It's a very basic, simple concept. It's the idea of hardware being designed to fetch multiple instructions per cycle, right? And we've seen that. You fetch multiple instructions per cycle, decode multiple instructions per cycle, execute, retire, finalize. So if you're n-way superscalar, your width is, let's say, n. And n could be 8 today. There are machines that fetch, decode, execute, finish 8 instructions per cycle. But the key thing here is the hardware has all the burden. Hardware is responsible for checking the dependencies between the instructions that are fetched at the same time. While you're decoding them, you should check the dependencies, and you should ensure that instructions that are dependent on others do not execute. So the complexity, the burden of dependency checking is in hardware. And when we talked about superscalar, I said that this is like multiple pipelines in parallel, except you need to do dependency checking, not only in the X dimension across the pipeline flow, but also in the Y dimension. Y dimension is when you have fetch multiple instructions per cycle, right? VLIW is a similar concept, except it puts the burden on the compiler or the programmer. Basically, you can still fetch, decode, execute multiple instructions per cycle, finish multiple instructions per cycle, and you have hardware support for that. But it's the job of the compiler or the software to pack instructions, independent instructions, in a larger bundle to be fetched and executed concurrently. So in the purest sense of the VLIW stands for very long instruction word. If you're fetching n instructions per cycle, the compiler guarantees that those n instructions are independent of each other, so that hardware doesn't need to do dependence checking. So it's a beautiful concept, and we will see the upsides and downsides of it. So hardware support is fetching and executing the instruction in the bundle concurrently. If the compiler guarantees that those instructions are independent, hardware doesn't need to do any dependence checking, right? In fact, VLIW in its pure form is all about finding instructions that are independent and scheduling them such that the pipeline, the hardware doesn't need to have dependency checking hardware or stall checking hardware at all. Hardware is very simple. Compiler does all the job. Of course, if compiler does all the job, as a programmer, you can do the job also, right? Basically, schedule instructions completely in software so that the pipeline can be very simple, no dependency checking logic. Exactly, basically, this is what I said. There's no need for hardware dependency checking between concurrently fetched instructions in the VLIW model. So you can think of this as like this, conceptually. You have some multiple execution units. These are processing elements, let's call them. And you go through some pipeline to execute them. And when you address a program counter, a location in memory, you're not getting just one instruction, but you're getting, in this case, 4 instructions. And the compiler guaranteed that these 4 instructions are independent of each other. Somehow the compiler ordered the code such that these are all completely independent. So it's beautiful. This way, the hardware doesn't need to do any dependency checking. And the compiler also does something else, which is it aligns the instructions such that instructions are aligned to the functional units that can execute them. For example, if not all of the functional units can execute a load, if this is the only functional unit that can execute a load, compiler ensures that load appears in the right place in the long instruction word, such that load can directly go into the execution unit. That eliminates some sort of network that you may imagine that takes the load. If, for example, if you put the load over here, and if the load execution unit was here, you need to somehow route that load here. But if load execution unit is here and the compiler is aware of that, and compiler puts the load over here, you don't need to do any routing logic in hardware. There doesn't need to be extensive wires to move one instruction to the processing unit that can process it. Does that make sense? So compiler is the master here. It does all the scheduling, and we'll see a couple of examples. And this was introduced by Josh Fisher. This is a very seminal paper. That introduced very long instruction word architectures, and he designed a processor that's called enormously long word instructions, 512 bits. The MIPS instructions that we're looking at are 32 bits. 512 divided by 32 is 8. So you can basically pack 8 instructions per cycle. Later, we will see that there were machines that were designed that can fetch 28 instructions per cycle. And of course, if you need a good compiler to be able to do that. Okay, so basically, what is a very long instruction word? It consists of multiple independent instructions packed together by the compiler. Packed instructions can be logically unrelated. One of them can be an add, load, multiply, divide. They can be completely unrelated to each other. And you will see the difference from SIMD or GPU-like architectures soon. In SIMD and vector processors, the difference is basically you can still fetch and execute multiple instructions per cycle, but the instructions need to be exactly the same. So basically, here, if you look, this is add, load, move, multiply. They're completely different, so you can pack them together and execute them. But in SIMD, single instruction, multiple data, well, it says single instruction, multiple data. You do the add on different data elements. It's the same add instruction on different data elements. You will see this later on. So that's the difference between VLIW and SIMD. So the idea is to have the compiler find independent instructions and statically schedule them into a single VLIW instruction, very long instruction. So traditional characteristics, clearly you need multiple functional units to be able to execute multiple things, very similar to superscalar execution. All instructions in a bundle are executed in lockstep. Again, the reason for this is the philosophy. The philosophy is hardware should stay extremely simple, software should do all the job of scheduling the instructions. If hardware should stay extremely simple, it should basically all of the instructions should finish before you move to the next instruction, because otherwise hardware needs to do some complex scheduling. That's the thinking. Although we will see that this is actually a downside of VLIW. As I said, instructions in a bundle are statically aligned so that you can directly feed them to the instruction in a functional unit. So if you think about this, the compiler needs to have intimate knowledge of how the machine looks like in this case. What is the pipeline? Where are the execution units? Basically, how many execution units do I have? What are the types of the execution units do I have? What are the kinds of dependencies in which I should insert no-ops, or I should find independent instructions so that the machine doesn't need to do any dependence checking. So a compiler needs to know the machine really, really well. And if you're the programmer, if you're not the compiler, you as the programmer need to know, if you're the assembly programmer, you need to know the machine extremely well to be able to program this sort of machine. So it's not easy to program, but if you develop a really good compiler, the compiler is able to reason about these things and able to schedule instructions such that it can find independent instructions across the entire program potentially. Okay, so let's take a look at an example. So assume that it's very similar to superscalar actually, except the compiler needs to somehow bundle these instructions. So you have load word and add bundled here, sub and and bundled here, or and store word bundled here. And there's no dependency checking logic compared to the superscalar, because the compiler ensured that these instructions are actually independent when it scheduled them. And if the compiler does a good job in the scheduling, you'll get 2 IPC, 2 instructions per cycle in this particular machine. Right? If the compiler is not able to find an instruction to bundle together with this one, for example, what will it do? It will insert a no-op. So you remember the no-ops from branch delay slots. Branch delay slots were a bad idea because it was trying to solve a problem with the compiler, and it was tying the ISA semantics with the microarchitecture. In this case, it's a bit different, right? In this case, basically, we're saying compiler should know everything that's going on in the machine and schedule the code. So the philosophy is a little bit more extreme, so it's more cleaner. It's cleaner than the branch delay slot. We can talk about that later on. Okay, so there's also lockstep execution, as I mentioned. If any operation in a VLIW instruction stalls for some reason, for example, you have a memory operation, all of the instructions in the bundle stall. So what does this mean? Basically, you have load, add, multiply, for example. If the load stalls for some reason, all of the other ones also stall. So you need to wait somehow. So there is some minimal stalling logic that you have to have, especially if you have memory systems in these machines. Yes?
Does the compiler assume, or how does it know how long each instruction takes?
So the compiler needs to know all of that, basically. Exactly. It's not, yeah, it's basically hard-coded into the compiler. There's a machine description that you feed into the compiler, and the compiler schedules instructions based on that description. It includes all the latencies and how long you need to wait. For example, if you have a load and then an add is dependent on it, how long should you wait before you schedule that add? Okay. So as I said, in a truly VLIW machine, this is really the purist's approach to VLIW, the compiler handles all dependency-related stalls. Hardware does not perform dependency checking. This does include also branches. So control dependencies are also somehow handled by the compiler, but we're not going to get into that. But the problem is, usually this is very, very difficult to do, and because you have variable latency operations, and compilers are not good at handling variable latency operations. For example, if sometimes your load takes 1 cycle because you hid in the cache, sometimes it takes 100 cycles. Now you have a problem. When you're statically scheduling code as the compiler, you don't know what to do very well. So these machines are usually have a lot of difficulty handling variable latency operations. As a result, they have not been as successful as out-of-order execution machines. So let's talk about the philosophy a little bit, because this is really about the execution paradigm. I don't want to go into a lot of detail. So if you're really interested, I'm going to point you to a lecture that talks about static instruction scheduling in VLIW machines. But philosophy of this is very similar to the reduced instruction set computer with simple instructions and simple hardware, except the ideas have multiple instructions in parallel. So it's actually even higher performance. So the original idea is actually even more extreme. It was first developed at IBM in the 1970s by John Koch, who was a Turing Award winner for the work he's done in compiler paradigms and also execution paradigms like VLIW. Basically, his dream, his vision at that time was to basically have the compiler to do everything, including the control signal generation. Basically, you don't really have instructions at that point. You have the bare machine with all of the control signals, and it's the compiler's job to orchestrate, map a program to all of those control signals. Right? This is, of course, very extreme, right? Because a machine can have tens of thousands of control signals, and you expose all of that to the compiler, and the compiler needs to somehow manage it and ensure that the program, higher level program, gets translated to those control signals. But it is possible, as you know, because we built everything from the ground up. You can imagine that this could potentially happen, right? Except it's not very easy to do, because now you're translating a very high level program into those control signals. The way we do it today is by abstraction layers. We translate the program into instructions. Instructions get translated into control signals, as we've seen in machine designs. But his dream was get rid of the instructions, directly connect the program into the control signals, and reorder these simple instructions, let's say. You can think of, actually, what are control signals? Control signals are actually micro instructions, right? When we talked about the micro-coded machines, we said micro instruction is really all of the control signals in the machine. So there are instructions at some level, except it's a very low level. So you can reorder all of these micro instructions for high performance. So as a result, hardware does little. Hardware is extremely simple in this case. It doesn't do decoding, it doesn't do translation, it's all the software's job to do that. Of course, this turned out to be very, very difficult to do, but it did lead to a lot of research in compilers, and it did lead to ideas in VLIW, which were more commercially viable. So in this case, we don't compile into control signals, we compile into simple instructions again, except compiler does the hard work to find the instruction level parallelism, schedule instructions, and hardware still stays as simple and as streamlined as possible. It still needs to translate the instruction into control signals. That's hardware's job. And it executes each instruction in a bundle in lockstep, as we discussed. And this still keeps the hardware simple. As a result, you can have a higher frequency and easier to design hardware probably, but the burden is now pushed to compiler. As a result, there's been a lot of work on compilers. I'll give you some history over here. So commercially, VLIW has been successful in some domains, but not so successful in the general purpose domains. We'll see what the reason was. So initially, Josh Fisher and Bob Rao were the two pioneers that designed these machines. So one of the first machines of the multi-flow company was 7-wide, and then they had a 28-wide machine. That's one of the widest machines that we know of that can execute independent, completely unrelated instructions. So GPUs today can execute, like vector machines, as we will see, can execute many instructions, except those instructions do exactly the same thing on different elements of data. But this is very different in the sense that you can pack completely unrelated instructions that are doing different things on different data. So actually, one of the processors, Transmeta Crusoe, was an x86 processor, and it had this compiler that translated the x86 programs into an internal VLIW format. So internally, they were executed as they had a VLIW engine. This was very, very interesting. They wanted to compete with Intel and AMD in terms of the speed of the x86 processors, but the overheads of doing this translation were not negligible. As a result, they didn't succeed, and I don't think they're around anymore. They tried to market their mechanisms as more energy efficient, which could potentially be true because you do this translation once, so you don't need to decode those complicated instructions many times. The compiler did that already for you, and if your internal VLIW instruction format is good, you can be much more energy efficient, but it's not clear if it worked out. So the most successful VLIW machines commercially are actually in embedded systems, digital signal processors and embedded processors, which we will also briefly talk about soon. If you know about TI's machines or Trimedia or STMicro, they actually are embedded processors. There you have programs that you can analyze well, and the compilers have been built to actually analyze them well to extract instruction level parallels. I'll briefly talk about Intel's effort in VLIW. So this was actually very interesting. When industry was trying to transition from 32-bit architectures to 64-bit architectures, so that you could have much larger address spaces as well as much larger data paths if you want. Some people were advocating taking x86 and making it 64 bits just by extending the ISA. The x86 is a very popular ISA. Everybody programs into it, right? There's a huge software base. So some people said, okay, we shouldn't change the ISA significantly. We should just add extensions. This is now known as the x86-64 architecture, which was initially advocated by AMD. Intel's solution at that time was actually completely change the ISAs. They actually wanted to take a huge different step. It was called IA64, Intel Architecture 64. And it was basically changing the ISA to be more VLIW, but not fully VLIW because they actually understood the problems with VLIW, which we will talk about, but it was based on VLIW principles. So it was called more explicitly parallel instruction computing, EPIC. Now, what does this mean? Basically, they figured out that it was very difficult for the compiler to pack many independent instructions into a single bundle. So they allowed the compiler to have some dependent instructions, except they asked the compiler to specify which instructions are dependent on which other to make hardware's job easier. So hardware still doesn't need to do full dependence checking. The compiler tells the hardware, okay, I'm sending you 8 instructions per cycle, but look, between 4th instruction and 5th instruction, there's a dependency. Now the hardware can actually see that, decode that quickly, and it doesn't need to check for dependency, trust the compiler, and order the instructions based on the compiler's instructions. So it's actually a very neat idea, I think, interesting idea. And they actually changed the instruction format because they actually designed a new ISA, instruction set architecture. A few bits in the instruction format specifies explicitly which instructions in the bundle are dependent on which other ones. Now, this didn't pan out. Why? Because this was a huge ISA change. People needed to change their software completely. And even though a company like Intel, who were actually dominating the processor design, they weren't able to change the ISA. So AMD's solution, x86-64, won, and Intel had to adopt AMD's solution, x86-64. Today, we have x86-64 processors, not IA64 processors. So IA64 is very niche right now. Some server processors have it, and I'm not sure if Intel is actually continuing this. So this is actually a very interesting history lesson. If you want to change the software stack completely, even if you're the dominant company in the world, it may be very difficult to do, and you may not succeed. But of course, since you have a lot of expertise, you can try this out, maybe lose some money, but you can still make some money by adopting somebody else's good solution, right? So it's good. There are a lot of interesting marketing and economics lessons, I think, related to VLIW. And that's why this is a very, very interesting concept. So people have actually tried to put VLIW engines in general purpose processors. Okay, let's talk about the trade-offs a little bit. We've talked about history, we've talked about the idea. So clearly, one trade-off is very obvious. There's no need for dynamic scheduling hardware. Out-of-order execution is not needed, assuming you have a pure VLIW machine. Simple hardware. Hopefully you get the benefits of out-of-order execution with the compiler with simple hardware. Of course, we will see that that's not the case when we talk about disadvantages over here. There's no need for dependency checking within a VLIW instruction, so there's simple hardware for multiple instruction issue and no renaming. Essentially, this is going into a little bit more detail. You get simple hardware in the end. So what does simple hardware buy you? Quicker design times, hopefully low power consumption, hopefully higher frequency design, if you can simplify the hardware. Again, as I said earlier, there's no need for instruction alignment or distribution after fetch to different functional units because the compiler knows the structure of the machine. It can schedule the code such that you don't need to do that distribution. This distribution network, we didn't talk about this distribution network, but in a superscalar machine, what might happen is, let's say you're fetching 8 instructions per cycle, and your load unit is here, and somehow your load is in this side of the bundle that you fetched in a superscalar machine. You need to somehow route that load over there. So you really need a crossbar network. We didn't talk about networks, and we're not going to have time to talk about networks, but you need to have an interconnect that can route all of these 8 instructions to all possible places in the machine, and that consumes a lot of energy, that adds a lot of complexity. So you get rid of all of that complexity with VLIW. It's actually a very beautiful, very clean idea, because it's really thinking about the machine completely from that perspective. It's very different from the branch delay slot. Branch delay slot is talking about just branches, very specific problem, trying to patch a problem, as opposed to having a principled approach. So it's a very principled approach. All of the machines exposed, and it's the job of the compiler to do everything. Okay, so disadvantages, as you've seen with the branch delay slot, the disadvantage is actually bigger here. The compiler now needs to find n independent operations per cycle, and you know by now what happens if it cannot find it. Well, it enters no ops. And this was a big problem with VLIW engines. But the fact that the compiler had to do that led to a lot of research in compilers, and that made compilers extremely good today. So the fact that people actually explored this approach enabled compilers to be extremely good at scheduling code. Maybe they're still not able to do everything, because variable latency is very difficult to handle. You have to do it with hardware. But if you don't have variable latency operations, if your code is mostly running out of the cache, or you somehow ensure that you get most of your code running out of the cache, you don't have a lot of variable latency operations. Compilers are very good at trying to schedule code today. So of course, if you have no ops, but then there are cases where you just cannot schedule the code because you don't have a lot of independent instructions, or there are other issues, then you lose parallelism and your code size also increases. Yes?
That would help with no operations actually work. Would they just be some instructions like a branch that never does anything?
Exactly. It's basically an operation that doesn't do anything. It doesn't change anything, but it just takes that cycle so that no other instruction can go in that cycle.
For example, branch not equal that looks at same register twice.
That's right. Yes, exactly. You can do that basically. You can repurpose some other operations as no operations. Yes. As long as you don't have any side effects, you don't change anything in the state. Okay, so one other issue with VLIW is, I mean, if your philosophy is that your compiler needs to adapt the code to the machine, then you basically have to say that I need to recompile when anything in the machine changes, right? This is a price you pay because of the principled approach that you've taken. So whenever machine's execution width changes in the next generation, you go from 4 byte to 8 byte, you go from 7 byte to 28 byte, well, you need to recompile the code, right? And also, whenever your instruction latencies change, whenever your functional units change. So this is actually a little bit heavy. Whenever something changes in the machine, you need to recompile your code. And if your philosophy is very, very pure, in the sense that the hardware doesn't do anything, then this compilation burden is very high, because anytime something changes in the machine, you need to recompile your code. This is very much unlike superscalar processing. So Intel, with their IA64, tried to fix this also. They actually tried to specify these bundles in a more flexible manner, such that you reduce the need for recompilation. And they actually had very good ideas in that, but it didn't work out in the end. So the lockstep execution also is a problem. It causes independent operations to stall. Basically, if you have load, add, multiply, and your load stalls, add and multiply, they're independent, they also stall. So no instruction can progress until the longest latency instruction completes. Later, VLIW machines relaxed this because they found out that that's a problem, and Intel IA64 definitely relaxed this very much. They basically stalled until the result of the instruction was needed. So they don't need to stall at the point when you execute the instruction. Yes?
Previously, you said that the processing elements, the instructions need to be aligned, so the processing element can process the instruction that it can process. What if we have a bundle of, let's say, 8 loads? It has to be done sequentially, but there are only 5 PEs that...
Yeah, same thing. The compiler basically ensures that you put only 5 loads in that case. If you have only 5 processing units for loads, you just put 5 loads at that time. And the 3 loads go in the next bundle. So think of this as compiler scheduling the code such that there is no conflict that happens in the machine, in the hardware. Okay, so basically VLIW simplifies hardware. I'm going to summarize, and then we're going to move on to the next topic. But it requires complex compiler techniques. So the solely compiler approach to VLIW has several downsides that reduce performance. Essentially, people figured out that there were too many no-ops because not enough parallelism discovered, especially in general purpose code. If your code is very specific and it has a lot of parallelism, this actually works really well. That's why embedded processors took advantage of this really well. And also, there is another reason why embedded processors took advantage of it, because they required less cost. So the hardware was a big deal in the embedded processors. Okay, the static schedule is intimately tied to the microarchitecture. So code optimized for one generation performs poorly for next if you're with changes. So you really need to recompile it to get performance. And there's no tolerance for variable or long latency operations. And we already discussed that. This is really the Achilles heel of all static scheduling techniques. If your latencies are variable, you really need to schedule dynamically, because you figure out your latency while the program is executing dynamically. If you already schedule your code with some latency in mind, it's just too late. You just cannot change that, right? That's the problem. Okay, the big upside, though, there's a big upside with VLIW. It actually enabled many compiler optimizations, as I said. Most compiler optimizations developed for VLIW are employed in optimizing compilers for superscalar optimizations, and they enable many code optimizations that are actually out there in all of the compilers today. For example, if you want to find independent instructions in code, you just cannot look at a code that is between branches. So remember, we looked at the control flow graph. You just have some number of instructions, 10 instructions. You really need to look at the code at a global scale. So modern compilers, what they do is they profile the code somehow, and they figure out which parts of the code are frequently executed. And on that frequently executed path, they assume that this is going to be executed, and they basically reorder the code that way. Now you look at hundreds of instructions, and now you can find instructions that you can reorder within those hundreds. And these techniques are developed mainly for VLIW compilation. Again, I'm not going to go into this in detail. We don't have time in this lecture, but it's fascinating. If you take a compiler's course, you will see a lot of these techniques, hopefully. And also, the other upside, I'm going to recommend some papers later on in the lecture. The other upside is VLIW has been very successful when parallelism is easier to find by the compiler clearly. So traditional embedded markets, digital signal processors, which had a lot of parallel operations to do, different types of parallel operations to do on the same data, they actually benefited from it. That's why the embedded market actually has a lot of VLIW processors. Some GPUs also internally employ VLIW formats. We're going to get into that next time when we talk about it, but that's not, so actually these concepts can be combined together. So this is one example work that was very influential, that essentially was initiated for compiling for VLIW techniques. And I cover this work in one of my videos that you can watch if you're interested. If you're interested in static instruction scheduling, this video talks about a lot of different static instruction scheduling techniques. And I mean, people have developed architectural frameworks for actually compiling for VLIW architectures as well. So if you're interested, you can take a look at these works. But that's all I have wanted to say about VLIW.